Welcome to the deep dive. So, think about something as basic as your hands left and right. They're mirror images, right? But you can never quite perfectly line them up.
That's chirality.
Exactly, chirality. And it pops up everywhere in nature. Snail shells, molecules essential for life.
It's fundamental.
But what if that handedness wasn't just fixed? What if it could actually, twist or change depending on which way you were looking?
Or maybe how aligned something was at a deep level.
Right. And what if space itself wasn't this smooth, uniform thing we usually imagine? What if it had a kind of texture?
A texture that changes depending on how you move through it.
Precisely. So today we're diving into a really fascinating paper. It's Hyperchirality in a Finsler Geometric Framework by Philip Randolph Lillian.
It's quite a piece of work.
It really is. Our mission today is to try and unpack these, mind-bending concepts, hyperchirality and Finsler geometry.
And see how they might just shake up our view of the universe.
Yeah, and it gets into some pretty wild, potentially real-world predictions, too. Okay, let's unpack this. Before we jump into hyperchirality, maybe a quick refresher on just plain chirality.
Good idea. So, as you said, it's that property where something can't be superimposed on its mirror image. Your hands are the classic example.
Left and right gloves, too.
Exactly. And in physics, this shows up with fundamental particles, especially with a property they have called spin.
Okay, so particles can be left-handed or right-handed based on their spin.
That's the standard picture. And what's really key there is that standard chirality is Lorentz invariant. Meaning it doesn't change no matter how fast you're moving relative to the particle. It's just set, left or right, a binary choice.
Like a switch.
Exactly. But this paper, well, it proposes something much more complex. It suggests that this simple binary choice can actually split. Bifurcate is the term used.
Bifurcate, like a fork in the road.
Sort of.
Yeah.
It suggests there might be more possibilities than just left or right-handedness under certain conditions.
Wow, okay, that's already a big leap. But you're saying to even talk about this, we need a different kind of geometry, not the usual stuff.
That's right. We're used to Einstein's general relativity, which uses Riemannian geometry.
Where space is, predictable, the rules are the same, whichever way you point, basically.
Right. Distances, angles, they behave consistently. But imagine a space where the feel of it, or maybe the distance you measure, actually changes depending on the direction you're going in.
Even if you're at the same spot.
Even at the exact same spot.
Yeah.
This is the heart of Finsler geometry.
Okay.
In Riemannian geometry, the mathematical tool that defines distances and angles, it just depends on your position. Let's call it x.
Makes sense.
But in Finsler geometry, the metric, often written f, x, y, depends on both your position x and your direction y.
Position and direction.
Yeah. And this framework, it naturally allows for things the paper calls anisotropic physics.
Physics changing with direction.
Exactly. And torsion coupling, which is about how a kind of twist in space interacts with things. And also coherence-driven bifurcations.
Okay, that last one sounds complicated.
It basically suggests that how internally aligned or coherent a field is can cause its properties, like handedness, to split.
Wow. Can you give an analogy, maybe?
Think of walking through a forest. In a normal Riemannian forest, the difficulty is just based on where you are. Maybe it's rocky here, swampy there.
Okay.
In the Finsler forest, the difficulty at the same spot might change if you're walking north versus walking east. Maybe there's a strong wind always from the west, or the undergrowth is aligned in one direction.
Ah, I see. The resistance, or the path itself, feels different depending on your direction.
Precisely. It's a direction-dependent landscape.
So this really means physics itself could be literally directional. That's a fundamental shift. It's not just smooth space anymore. It has texture.
That's a good way to put it, a directional texture.
Okay, so now we have this direction-dependent playground, this Finsler geometry. Let's get back to hyperchirality. How is it formally defined in this context?
Well, the paper describes it as a higher dimensional generalization of chirality.
Right.
Where the handedness of a field like one of these particles or waves can actually split or bifurcate, like we mentioned.
And that split depends on
its direction of motion or potentially its state of internal coherence.
Coherence, like how aligned its internal bits are.
Sort of, yeah. Think of it as a measure of its internal order or unity. So a hyperchiral spinor, that's the name for these fields, is something, let's call it CX chi y, living on this Finsler manifold.
Psi of position and direction. Got it.
And there's a special mathematical tool, an operator, called a hyperchirality operator, let's label it gamma h hat, that acts on this field to determine its handedness.
Okay, and what's special about this operator?
It's built using new kinds of gamma matrices, fundamental objects in particle physics, but these ones are also direction-dependent.
So everything's getting direction-dependent here?
Pretty much. And this operator is designed to capture how handedness can twist or split based on that coherence idea we talked about. It reflects what the paper calls torsional bifurcation embedded in coherent split hyperspinor bundles, which is a mouthful, I know.
Yeah, just a bit. But what's the upshot? What kind of handedness does it reveal?
This is maybe the most striking part. Standard chirality gives you a +1 or a -1, left or right.
The binary switch.
Right. But the result of applying this hyperchirality operator can be -1, 0, or +1.
0. What does 0 mean? Neutral.
Exactly. It introduces a neutral state of handedness, a state that's neither left nor right, maybe a perfectly balanced state or something in transition.
So not just left or right, but maybe in between or neither, tied to how you're moving or aligned in this directional space.
Precisely. It adds a whole new layer of nuance. Direction isn't just a coordinate anymore. It's affecting the very nature of matter.
Okay, that's fascinating. But how do we even, construct these hyperchiral spinors? Where do they come from in this Finsler space model?
Good question. So these spinors, here's why. They don't just live in our usual 4 dimensions of spacetime. They transform under a larger symmetry group called SO1 3 plus N.
Uh-oh, more dimensions. The N implies extra dimensions.
It does. It suggests these fields inherently exist in a higher dimensional space than the 4 we directly perceive. And as we said, their gamma matrices are direction-dependent too.
So even basic interactions could change with orientation.
That's the implication. And like any field in physics, their behavior, how they move, interact, their energy is governed by a Lagrangian.
Right, the kind of rule book for the field.
Exactly. It has terms for kinetic energy, how it moves, interaction terms, how it couples to other fields or the geometry, and mass terms.
Standard components, but presumably built within this Finsler framework.
Yes, adapted for this direction-dependent geometry.
And I assume they have their own special symmetries controlling those interactions, like forces in the standard model have gauge symmetries.
Absolutely. The paper proposes a new gauge symmetry it calls hyperhosin. This symmetry group is sort of embedded within that larger SO1 3 plus N space we mentioned. Yeah. And it's responsible, according to the paper, for the torsional and coherence field couplings in hyperspace.
So this new symmetry directly links the fields to the twists, the torsion of space, and also to their coherence.
That's the idea. The gauge fields associated with this symmetry, the force carriers, if you like, actually incorporate corrections due to torsion. It directly ties the geometry's twistiness to the field's behavior.
Wow. A really deep connection between the shape of space and the properties of matter. Okay, so if these fields exist in this twisting directional space, how do they actually behave? How do they move?
Right, the dynamics. So in Finsler geometry, you have generalizations of the concepts of curvature, how space bends, and torsion, how it twists.
We talked about torsion being like a corkscrew property.
Yeah, that's a decent analogy. Mathematically, it measures the failure of the connection to be symmetric. But physically, the paper links it to an underlying coherence twisting of the fields within space.
Yep.
And the actual equations of motion derived from that Lagrangian we mentioned tell you exactly how these hyperchiral spinors propagate through this complex manifold.
Is there a simpler example? It's getting pretty abstract.
Yes, thankfully. The paper provides a toy model to make things more concrete. It considers a spinor moving in a 4 plus 1 dimensional Finsler manifold.
So our usual 4 dimensions, 3 space 1 time plus 1 extra.
Exactly. And this extra dimension, often labeled Y5, is interpreted as representing a coherence direction.
Ah, tying back to that coherence idea.
Precisely. And the Finsler metric in this toy model looks something like F squared equals the standard spacetime distance squared, plus a term involving this extra direction. Alpha x times y5 squared.
Okay, so the distance measurement gets modified depending on your velocity or orientation in this 5th coherence dimension.
That's the essence of it. And this leads to a really interesting consequence for energy and momentum.
The dispersion relation.
Exactly. The relationship between energy, E, momentum, P, and mass, M. In this toy model, it comes out as E squared equals P squared plus M squared.
That's the standard relativistic part.
Right. But then there's an extra term, plus alpha x times P5 squared.
P5, momentum in the 5th dimension.
Momentum associated with that coherence direction, yes. And alpha x is a factor that might vary depending on where you are in space.
So, wait, This means the energy of a particle doesn't just depend on its mass and its regular momentum.
Correct. It also depends on its momentum or alignment in this extra directional coherence dimension.
So the energy of a particle could literally change based on its direction or how coherent it is. That is wild, like hidden energy costs or gains depending on how you travel through this textured space.
It's a profound implication, definitely.
Now, this all sounds incredibly theoretical. Finsler geometry, hyperchirality, extra dimensions. But you mentioned the paper actually suggests places we might see this, real-world effects.
It does, yes. Which is crucial, of course. The idea is that these hyperchiral fields represent matter-energy coherence configurations aligned with directional torsion.
Okay, basically matter whose alignment interacts with the twist of space.
A good summary. And potential observable signatures. Well, they suggest looking for anomalous polarization in the cosmic microwave background.
The CMB, the afterglow of the Big Bang, so unusual patterns in its light.
Potentially direction-dependent patterns, yes. Another is neutrino spin anisotropy.
Meaning neutrinos might prefer a certain handedness depending on which way they're going.
That's the idea. Neutrinos are already known to be purely left-handed in the standard model, so any deviation, especially a directional one, would be huge.
What else?
Possibly parity-violating dark matter fields, dark matter that interacts differently with left versus right-handed systems in a way that depends on direction. Or even effects here on Earth, like coherence torsion emissions in condensed states, specific materials perhaps emitting signals related to this torsion.
Condensed matter like crystals or superconductors.
Could be, yes. And then, specifically from that toy model we discussed.
With the fifth dimension.
Right. It predicts subtle angular deviation in gravitational lensing.
So light bending around massive objects might bend slightly differently depending on the path?
Possibly, if the path goes through regions with significant directional texture or torsion. And also potentially unique neutrino spin correlations related to that fifth dimension.
These aren't just vague ideas, then. They're pointing towards actual experiments, things astronomers and particle physicists could potentially look for?
That seems to be the goal, yes.
Yeah.
To provide testable predictions.
Okay, so connecting this to the bigger picture, how does this whole framework, hyperchirality, Finsler geometry, fit with what we already think we know, like general relativity, the standard model? Does it throw them out?
That's a really important question, and the paper seems to position this not as a replacement, but as an extension.
Okay, how so? With general relativity?
Well, Finsler geometry naturally includes GR's Riemannian geometry as a special case, the case where direction doesn't matter. But it goes further by naturally incorporating torsion, that twistiness, into the description of spacetime curvature itself. It extends the geometric language.
And the standard model of particle physics?
In the isotropic limit, again, where direction doesn't matter, the paper states that these hyperchiral spinors should just reduce back to the familiar Dirac spinors we use in the standard model.
So it contains the standard stuff as a baseline.
Exactly. It adds new possibilities without necessarily contradicting the successes we've already had.
What about more speculative theories, like string theory or loop quantum gravity?
Ah, interesting point. The paper draws connections there, too. Concepts like hyperdimensional symmetry and torsional compactification within this framework.
Compactification, like rolling up extra dimensions.
Sort of, yeah. The paper suggests these correspond to what string theorists call moduli parameters defining the shape and size of extra dimensions. But here they're called coherent split moduli, implying that the coherent state of these hyperchiral fields could actually influence the properties of these extra dimensions.
So the state of matter could affect the shape of hidden dimensions.
That seems to be the connection being drawn. It attempts to link the internal properties of fields with the geometry of higher dimensions.
So it's not just a standalone idea, it's trying to act as a potential bridge, connecting GR, particle physics, maybe even quantum gravity ideas.
That definitely seems to be the ambition. In fact, the author frames it as a cornerstone of a larger theoretical framework they call the hypersymmetric coherent resonance theory of everything. HHHCR-TOE for short, I suppose. Well, it aims to unify physics using these principles of coherence, symmetry, and resonance. There's talk of a coherence tensor and its eigenvalues playing a key role, showing how chirality itself can split or bifurcate across different hyperdimensional modes linked to torsion resonance.
Okay, so resonance and coherence become really fundamental principles driving how handedness manifests.
That appears to be the central theme of this broader theory, yes.
Wow. Okay, so today we've really gone on quite a journey. We started with the familiar idea of left and right hands, chirality.
And ended up in a universe where direction fundamentally changes the rules.
Yeah, diving into this direction-dependent Finsler geometry and this really wild concept of hyperchirality, where
Yeah.
handedness isn't just left or right, but can split, maybe even be neutral, tied to direction and this idea of coherence.
And based on potentially higher dimensions and new symmetries.
It really shows how thinking about geometry differently, using new mathematical tools, can just completely unlock new ways of imagining the fundamental forces and particles, doesn't it?
It pushes the boundaries, absolutely. It's a reminder that our understanding is always evolving.
It really is. So here's a final thought to leave you with. If the very fabric of reality, its geometry, the basic properties of matter like handedness, maybe even energy, truly depends on the direction you're looking or moving.
Or how coherent things are.
Right. What might that imply about the nature of observation itself? Does looking in a certain direction or interacting in a certain way subtly change the reality we perceive? And what does that mean for our place in what might be a truly anisotropic universe?